Hello, I'm Alan Rosas, and this is a video for my Math 2D discussion for UCI's Fall 2025 quarter. Today, I'm going to be discussing problem 49 from James Stewart's Calculus in section 10.1. And the problem reads as follows. Let P be a point at a distance d from the center of a circle of radius r. The curve traced out by P as the circle rolls along the straight line is called a trochoid. Think of the motion of a point on the spoke of a bicycle wheel. The cycloid is the special case of a trochoid with d equaling r. Using the same parameter theta as for the cycloid, and assuming the line is the x-axis and theta equals 0 when P is at one of its lowest points, show that the parametric equations of the trochoid are as follows. And they give us these parametric equations here, that x is equal to r theta minus d sine theta, and y is equal to r minus d cosine theta. They also want us to sketch the trochoid for the cases d less than r and d greater than r. So for this problem, I won't be sketching the curves by hand because I plan to present them on Desmos, which I think will give us a better feel for what these curves look like in general, and it will also give us the geometric setup that we will need to work with to be able to derive these parametric equations. So without further ado, let's go ahead and jump to Desmos. So here we are in Desmos, and we're going to be taking a look at these trochoids for different choices of d and r, and seeing what the resulting curves look like. So you might notice right here in Desmos, I have plotted out a circle whose center I've labeled center and colored green, and I've labeled the point P with colored red, and that point P is going to be drawing out our curve as we let the circle roll forward. Now, if you haven't seen the cycloid before, so I'm going to be specific and not talk about general trochoids. The cycloid, which I have set up in Desmos here, is the curve that you get when you fix a point on a circle that's rolling and you see which curve is sketched out as you trace out the path followed by P. And here's what I mean by that. So I'm going to hit play on this parameter T final. And you might notice, it's really pretty, that we get this U-looking curve as the circle rolls around, but we focus our attention on where P is going as the circle rolls around. This curve right here that's drawn out in this way is called a cycloid. And the trochoid is just a generalization of a cycloid in which the point P that we're considering doesn't need to lie on the circle anymore. It could lie on the outside of the circle, which for example happens if I increase d to be, say, 1.5. It just has to be bigger than the radius r, which in my case is 1 right now. And when we do this, what we find is that the curve becomes a lot more stretched out, if you will. And it actually goes below the x-axis too, which should make sense because now that we have increased the distance d greater than the radius of the circle r, but the radius of the circle r is the distance from the x-axis to the center point in green. The point in red, which is the point that's tracing out our curve, should overshoot that distance and actually go below the x-axis. Likewise, if we reset the curve to 0, but now we make d smaller than r, so r is 0, r is 1, and d is now 0.5, we get a different looking curve. One that looks a lot smoother and doesn't overshoot the x-axis, unlike the case where d is bigger than r. And once again, the cycloid is the special case where d is exactly the radius, and therefore our point P is actually on the edge of the circle, and hence it traces out the path that P follows as the circle rolls on the flat x-axis. So this is pretty cool in my opinion, and I'll be providing this Desmos link in the description if anyone is interested. But for now, now that we've gotten a feel for what these curves look like in general, let's turn back to our original task of trying to find or derive the parametric equations for these types of curves, trochoids. Okay, welcome back. So once again, our goal is going to be the derived coordinates for this point P right here in terms of the parameter theta that they used in the cycloid, as said in the problem statement. Now, the specific parameter they're referring to, and if you want to see this for yourself, this is actually one of the examples in the book. The parameter theta that they're referring to here, the same one that they use for the cycloid, it's going to be exactly this angle right here. So this is our theta. So if we let P, our point P, have coordinates x, y for now, our goal is to express x and y both as functions of theta. And now let's go ahead and add a few more labels. So recall that our circle has radius r, so this is going to have radius r. And the distance from the center to P was called d. So this will be d. And because r and d appear here, it's natural to expect that our expressions for x and y are going to depend on d and r, and that's exactly what we see if we go back to the problem statement. X is a function of theta, but it depends on r and d, and likewise y is a function of theta that also depends on r and d. Now, the first stepping stone to making progress with this problem is going to be to draw a very special right triangle that appears in this diagram. And let me go ahead and give it to you all. So if I draw a vertical down all the way until I get to the center of the circle here, and then I draw a triangle to the right, what we see is that we have formed a right triangle in this diagram. Now, anytime we have right triangles, it's always a good idea to use some trigonometry. And to this end, let me go ahead and label the legs A and B respectively. And now that we've drawn this right triangle, let's go ahead and give a name to this smaller angle right here. Let's call it tau. Tau's a good name. Okay. Now, remember what we're trying to do. Our goal is to find expressions for x and y that only depend on theta and perhaps on d and r. And it will be helpful in what follows if we remember what x and y are in terms of this whole coordinate system that we have right here. So x is just the distance from the origin all the way to the point x. So if I take a pen and draw a line all the way to where x is, it's roughly around here, then this whole length is equal to x. Similarly, if I start at the origin and walk all the way up until I get to the point y, then the corresponding distance right here, well, that's going to be the y coordinate for P. Okay. So why am I bringing this up? Well, first thing to notice is that we can express y as this length A right here plus, and this is where we have to do a bit of thinking. If we think of taking this radius here from the center to the edge of the circle and just dragging it over here, so it's just underneath this green line labeled A. And let me go ahead and draw a copy of that line right here for us. So that is r. Then what we see is that the length y, the y distance, the y coordinate that we care about, is exactly the sum of the length a plus the sum of the length r. Let's go ahead and write this down because this is important. Y is equal to a plus r. Now we can play a similar trick with x, but here we're going to need to do some subtraction instead. So, okay, x is this length right here. The length from this point right here to this edge, well, if we look at our triangle right here, we can see that it corresponds with this side length b. So if we draw a copy of that line down here, that distance is also equal to b. And, okay, how do we relate this? So we've drawn out x and b here, but we need to get, for this to be useful, we need to get an expression for the entire length up to this point. And this is where we have to remember that we are letting this circle roll. And that's the key insight that's going to let us figure out what the whole length has to be. So let me give this whole length a name. Let's call it L. Now the circle is rolling. So that means, well, hopefully everyone can see that this point right here, which is between our point P and the center, that's the point that started originally over here at the origin when the circle wasn't rolling. So what that means is that the length of this arc right here, which I am coloring in purple, because the circle is rolling, the length of that arc must be equal to the total length that it has covered on flat ground. I hope everyone can see that. But, okay, what is the length of that arc? Well, here we need to remember some trigonometry. And let me write this down. Or it's more of a circle fact. Let me label it as such. So the fact that we're going to use the length of the arc, and let me do this in purple. The length of this arc is the radius r multiplied by the measure of this angle here when measured in radians. And it's important that this angle be measured in radians, otherwise this length formula doesn't work anymore. But we know what this angle is. This angle is our parameter theta. So the length of the arc is r times theta. But as we've already mentioned, we know that L is equal to the length of that arc, and therefore L is equal to r times theta. But now, because from this part of the diagram down here, we know that L is equal to x plus b. L is equal to x plus b. What this tells us is that x has to be, give me a sec, L minus b, or r theta minus b. Let's jot this down up here as our next equation. And now all that remains is to figure out what a and b have to be. And this is exactly where trigonometry is going to come into play. So let's remember the triangle that we drew here in green. This right triangle has the lengths a and b that we care about. And to find those lengths, we just need to use SOHCAHTOA. So the length a, using trigonometry, well, we labeled this angle right here for our right triangle tau. So it follows that a is going to be the hypotenuse, which is d remember that d is the distance from our point P to the center, times the sine of tau. Oh, sorry, not pi, tau. Similarly, the length b down here is going to be d times the cosine of tau. And therefore, we can rewrite our parametric equations as y is equal to r plus d sine of tau. So note that I just rearranged a and r. I swapped their order. So now instead of a plus r, it became r plus a. And then I substituted my expression for a. And similarly, x is equal to r theta minus d cosine of tau. And all that remains to finish up with the equations that we want is to rewrite this angle tau that we have in our trig functions in terms of theta. But how do we do this? Well, this is where the next bit of insight comes in. If we remember, we said that theta was this whole angle right here, and tau was the small angle. But you might notice that we have a right angle right here. And right angles in radians have a measure of pi/2 radians. So what we know now, because theta is this right angle plus this smaller tau angle, we know that theta is equal to tau plus the right angle in radians, which is pi/2, which says the same thing as tau is equal to theta minus pi/2. So our equations over here are going to become y equals r plus d sine. Now we just plug in our expression for tau, theta minus pi/2, and x is equal to r theta minus, my apologies, d cosine theta minus pi/2. But recall, or you might remember from Calculus 1 or elsewhere, that whenever we subtract inside of a function, so by a positive number, in this case we're taking sine and we're taking its input and subtracting by pi/2, the positive number pi/2, the effect that has on its graph is to shift it over to the right by a distance of whatever it is you're subtracting by. When you sketch out the graph for sine and you do this, what you end up with is the graph for, it would be negative cosine, sorry. And let me illustrate this over here off to the left. So if we take our function, sine of x, so this is sine x, and now we shift it over to the right by exactly pi/2 radians. What we're going to get looks like a cosine graph, but it's flipped over because normally the cosine has a value of 1 at 0, but here it has a value of -1. So this graph is exactly negative cosine x. And so what this means is that, let me make some space here. Let me try again to make some space. What this means is that y can be expressed as r plus d or minus d cosine of theta. R minus d cosine of theta. And similarly, when you take cosine and you shift it over to the right, so now let's go back to the left side, and now let's draw the ordinary cosine, the one that's not negative. Shifting over its graph to the right by pi/2, we're going to end up with, well, it's just going to be the graph of sine. And so another way to write x is r theta minus d sine theta. And if we go back to the problem statement, these are exactly the equations we wanted to obtain. And we're done. If there's any questions about this problem, please feel free to drop a comment. Otherwise, I will see you all in the next video.